right, work. Work is going to tell us how forces change velocities or change the energy of a system. It's going to be the bridge between what a force is and energy. Energy is a scalar quantity, which means it doesn't have a set direction. You can't say, I have 50 joules of energy left or 50 joules of energy right. It doesn't have an energy, it doesn't have a direction like that. It's kind of like temperature. It's whatever temperature it is. It's not up or down or left or right. So work is the bridge between force and energy energy is something we'll come up with a little bit later. As far as the actual value for work, it's calculated with the following equation, F delta x cosine theta. W is work. F is the force in newtons. Change in x is the displacement of the object. So we're talking about how much the energy of a single object changes. So we need to know how far that object moved. And also, did it move in the direction of a force? Or did it move perpendicular to a force? Or did it move at an angle with that force? Because that will determine the work done as well. Now, right away, you're going to have to get out of your head your idea of work. What you guys think of work is not exactly what physics people think of work as. For instance, picking up a book and carrying it across the room. If this book is resting on the table and I pick it up, I did work picking it up. But when I walk around the room with it, if I don't change its height, this actually requires zero work. In physics terms, a work is only done when you have to apply a force in order to do something. And you move in the direction that you're applying the force in. If I'm holding a book like this, in what direction am I applying the force? Up. And if I walk around the room, I'm moving it left and right. So I don't have to apply a force in the left or right direction in order to keep the thing moving. If it's moving at a constant velocity, I don't have to apply a net force in order to make it go. So by definition, I don't have to do any work in order to keep it moving. You'll see the little nuances as we go through it. The units of work is the joule, named after Joule, James Joule, Henry Joule. I don't know what Joule. Somebody Joule came up with work, and I think he did it with engines, but it applies to engines, it applies to moving objects, it applies to a number of different things, as you'll see. It's a Newton times a meter, so it's a Newton meter. James Prescott Joule, thank you very much. It is a Newton meter, and if you look back at the formula, force is in newtons, distance is in meters, so a joule is a Newton times a meter. Cosine theta doesn't have any units on it, so that's not important. Just to give you an idea of how much a joule is, when I apply 1 Newton over a distance of 1 meter, I use 1 joule of energy. So if you think of an apple as weighing 1 Newton, if I pick up an apple from the floor and raise it up 1 meter, that's 1 joule of energy that's being consumed or used or whatever. When we get to nuclear physics, we're going to use a different unit of energy called an electron volt. That's much more useful when you're talking about subatomic particles. Instead of talking about energies which are, say, 10 to the negative 16th or 10 to the negative 20th, we just use a different unit for it, so it's a little bit more convenient for us. Plus, when you're moving around electrons, well, let's not get ahead of ourselves, but when you're moving around electrons, it makes a whole lot of sense. Important, 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 because they're absolutely going to ask you this. If a force doesn't cause a displacement, then that force is not responsible for doing any work. Again, with the book example. If I ask you how much work the force of gravity did, the answer is 0, because gravity is acting perpendicular to the motion. Gravity is up, the motion is left and right. And if you trust the equation, force is up. Let's say I apply 10 newtons of force upwards. And let's say I move it around for 10 meters. Well, if force is up and displacement is in that direction, what's the angle between those two vectors? It's 90 degrees. What's cosine of 90? It's 0. So the work done in that case is 0. The force, in order to do work, has to be directed in some way in the same direction as the displacement. If any part of that force is in the direction of displacement, then work was done. So suppose instead of pushing it left and right, I kind of lifted it at an angle. So I did this with it. Now, cosine of 45 is going to be some value. So that force would have done some work in that case. Not 100% of the work. Cosine 0 would be maximum amount of work, but just a portion of it. Hopefully you'll follow that more when we go through some examples. Unlike forces, work can be a positive value or a negative value. It can also be 0. So forces can apply or do negative work. Positive work would be gaining energy. Negative work would be taking away energy. And 0 work would be not changing the energy at all. Looking at the example of an object on the flat floor before we get to that. Say I'm pushing the object at constant velocity. What forces do I have on that object? Gravity, normal force, push, friction. I have 4 forces on that, and each one of those forces can do work, or not do work, or do negative or positive work. If we look at the normal force, is that doing work? No, because it's perpendicular to the direction of motion. So normal force, work done by the normal force is 0. Gravity. Does gravity do any work in this case? No, because it's also perpendicular to the direction of motion. So its work is also 0. Force of the push. Does it do positive, negative, or 0 work? It does positive work because it is in the same direction as the displacement. And friction? Friction would do negative work because it is in the opposite direction. And again, if you trust the equation, friction is how many degrees away from the direction of motion? 180. Cosine of 180? Negative 1. So you end up with negative F delta x for the work. So that's negative work. Follow? Questions so far? Example. Man holds up a 50-kilogram box at arm's length for 2 hours as he is standing still. How much work does he do on the box? 0. There's no displacement to begin with. So work equals F delta x cosine theta. Displacement is 0. The whole thing goes to nothing. So you got to be moving. You have to have a displacement in order to have work done. If a man holds a 50-kilogram box at arm's length for 2 hours as he walks 1 kilometer forward, how much work does he do on the box? Let's just take a look at this. Be sure everybody's on the same page. That's a hand. Sorry. Holding the hand. He's not holding the hand. He's holding a box. And he walks for 1 kilometer forward. He's got all these different forces that are on the box. He's got to have a push force, right? Otherwise, he's not starting it. Now, once he moves up to a constant velocity, the box, he's walking at, say he walks at 1 meter per second. Once he gets going, that box is also moving at 1 meter per second. So he doesn't have to apply these forces anymore. So he doesn't have to push it anymore. Once he's up to that speed, the box will continue going on that speed forever. Not law of inertia. So what we're left with is a normal force in mg. The question says, what work does he do on the box? So we need to know which force he is applying. Which force? He applies the normal force. So the question really states, how much work does the normal force do on the box? Because that's what he's doing. Work equals F delta x cosine theta. The force, normal force, is going to be equal to mg in this case, times the distance traveled, 1,000 meters, times the cosine of the angle between displacement and force. There's displacement, there's force, cosine of 90, work is 0. It's not always going to be so obvious what the angle is. You're going to have to maybe do some trig or some triangle math in order to figure out what exactly the angle between the force and the direction is. For instance, if you're pushing an object up a hill, or if you push an object not exactly up the hill, but into the hill. If you push an object into a hill hard enough, it's going to go up the hill, right? So this is the displacement. This is the force. You have to ask yourself, what's the angle between? It's whatever the angle of the hill is in this case. But it's just not always going to be obvious, and that's the point. This is pretty straightforward. It's 90 degrees. But just be careful. The angle represents, theta is between F and X. Not necessarily what they give you in the problem, but what's between the force and displacement. If a man lifts a 50 kilogram box 2 meters, how much work does he do on the box? Again, good idea to start with the picture. If you don't get one, draw a picture. FBD, even though we're dealing with work, we're still dealing with forces, and whenever you deal with forces in FBD is a good idea. If he lifts it up, how much work does he do? Again, what force does he use? He applies the normal force. So how much work does the normal force do? Normal force, change in x, cosine theta. We'll assume the acceleration is 0 in this case. Normal force is equal to the weight of the object. He raises it 2 meters. What's the angle between force and displacement? 0? You don't have to include that if it's 0. Mass is 50. Gravity, 50 times 10, 500 times 2, 1,000, and the unit of work, joules. So he applies 1,000 joules of work to that box. Before we go along, how much work does gravity do? Negative 1,000. Gravity's force is still this. But what's changed? The angle between the force of gravity and the displacement. Displacement is up this way. So the angle between those two things is 180, becomes -1, and so -1,000 joules. Did the box gain energy? Normal force did 1,000 joules, but gravity did -1,000 joules. What happened to the total energy of the box? Now, it actually increased its energy value. In this work calculation, we're talking about what work that forces do, not the energy of the box. They're different. You can't simply add the works done by each force and get the total amount of energy. We'll get into that a little bit later, though. We need to